Welcome to The Explainer. Today, we're diving into a totally new way AI is learning to write. And look, this isn't just some small tweak. We're talking about an approach that could be the biggest architectural shift since the transformer model itself. Seriously.
Okay, let me start you off with a question. For years, right, AI has basically been a painter. It adds one word at a time, like a single brushstroke, to build a sentence. But what if it could be a sculptor instead? Imagine starting with just a block of random, staticky noise, and then chiseling it down until a perfect, coherent sentence just emerges.
And that right there, that's the setup for the two big ideas competing in text generation today. You've got the reigning champion, the painter, that's your autoregressive models, like the GPT family. And then you've got this new challenger, the sculptor, and that's what we call diffusion language models.
All right, so before we get into the new stuff, let's do a super quick refresh on the reigning champ. I'm talking about the models we all know and use every day. How do they actually work?
So it's a pretty straightforward but, incredibly powerful process. The model sees the cat sat on the, and its whole job is to predict the very next word. Matt, probably. It just does this over and over, one word at a time, sequentially. And hey, this method has gotten us unbelievably far. But, and this is a big but, it has some pretty deep-rooted limitations that we're about to get into.
Okay, so now let's talk about the new kid on the block, the challenger. These diffusion language models, or DLMs for short, are a totally different beast. They represent a complete paradigm shift in how we even think about generating text.
You see, instead of predicting the next word, DLMs kind of work backwards. It's wild. They learn by taking a perfectly good sentence, and then they just destroy it. They systematically add noise or corruption step by step. Then they train a model to get really good at reversing that damage. So once it's trained, you can give it pure, random noise, and it knows exactly how to denoise it back into a brand new, clean, coherent piece of text.
And look, this isn't just some wacky idea from a research lab anymore. Not at all. The last year has been an absolute watershed moment for this tech. We've seen foundational papers win Best Paper at major conferences, we've seen big open source models get released, and we've even seen Google's model hit commercial-grade performance. This thing is real and it works at scale.
So, you're probably wondering, how does this sculpting thing actually work under the hood? Well, it's this really fascinating two-part process that honestly feels a little backward when you first hear it. What's so cool about this is that the model has to learn how to break something before it can learn how to build it. Think about it. In that forward process, it's just corrupting text. Then, in the reverse process, it's training to undo all that damage, step by step. So once it's an expert at fixing things, you can just hand it a pile of random junk, pure noise, and it can apply that same undo process to create something totally original.
Okay, so this is the absolute key takeaway. The fundamental difference here is the mechanism. Autoregressive models are causal. They only see what came before. But diffusion models, they're holistic. They see the entire messy sentence, the whole context, at every single step. And that lets them refine the whole thing at once. It might sound like a small distinction, but trust me, it unlocks a whole new world of capabilities.
All right, so now that we know how they work, how do they actually stack up against each other? Let's get to the tail of the tape. What are the big advantages and, the big weaknesses?
Well, the first big win for the sculptor is speed. A painter has to add one brushstroke at a time, right? But a sculptor works on the entire block of stone at once. It's the same idea here. Diffusion models can generate whole chunks of text all at the same time, instead of going token by token by token.
And we are not talking about a minor speed bump here. This parallel processing is a massive accelerator. Get this, Google's Gemini diffusion clocks in at almost 1,500 tokens per second. That is a staggering 5 times faster than similar autoregressive models. That's a huge deal.
Okay, next up, context. Because these models see the whole sentence at once, they get context from both directions, what comes before and what comes after a word. This is a game changer for stuff like editing, and it helps them crack a really tricky classic AI problem called the reversal curse.
And this is a perfect illustration of what I mean. If you train a typical autoregressive model on the phrase A trained B, it gets weirdly stuck. If you ask it to reverse that, it really struggles to say B was trained by A. It's this strange little quirk of its one-way, forward-looking brain. But diffusion models like LLaDA, with that holistic, all-at-once view, no problem. They can flip those associations around easily.
And that same holistic context, makes these models surprisingly good at really structured things, like writing code. I mean, on the live code benchmark, Gemini Diffusion is already outperforming its super optimized autoregressive cousin, Gemini Flashlight. That's a pretty big statement.
But of course, the new challenger isn't perfect. There's a flip side. You know that slow, methodical, step-by-step thinking that makes autoregressive models, well, slow? Turns out that's actually their secret weapon when it comes to really complex, multi-step reasoning.
Yeah, you can see that performance gap pretty clearly on benchmarks like GPQA Diamond, which are built specifically to test that kind of deep reasoning. So for now, when it comes to solving really knotty problems, the painter's methodical, step-by-step approach still comes out on top.
And it's not just about reasoning. There are some serious engineering hurdles to clear here. Right now, these diffusion models are just more expensive to train and run. They're also a lot trickier to tune just right. And a big one is that our entire infrastructure, things like key-v caching, was built to make the old sequential models faster. It's just not optimized for this new all-at-once approach.
So, you've got this intense competition heating up, which begs the question, where is all of this going? What's next for language models? It really feels like we're at a major turning point. I mean, the whole field is just exploding with innovation right now. You've got the big industry labs like DeepMind pushing the performance envelope. You've got academia like Stanford laying down the fundamental theory. And you have critical open source projects like Llama making sure everyone can get their hands on this tech. But maybe the most interesting part? People are already building hybrid models that try to combine the strengths of both.
And all this fast-paced progress is definitely turning heads. When Google's Gemini Diffusion finally caught up to the top autoregressive models in performance, a principal scientist there, Jack Ray, called it a landmark moment for the field. And that's a pretty clear signal that, yeah, this technology is absolutely here to stay.
And when we look to the future, the unique skills of these diffusion models open up some seriously cool possibilities. Because they generate everything at once, they're a perfect fit for multimodality. I'm talking about generating text, video, and audio all at the same time, seamlessly. They're also showing huge promise for scientific discovery. And maybe, just maybe, once they get more efficient, they could be the engine that powers truly real-time conversational AI.
Which leaves us with the big final question, right? As these two incredibly powerful approaches continue to get better and better, is this a winner-take-all situation? Will one of them eventually replace the other? Or is the future of AI not actually a battle at all, but a partnership, a powerful collaboration between the meticulous painter and the visionary sculptor?